Hello, this is Mrs. Leahy. Let's talk about probability distributions. But first, let's go ahead and discuss a little activity. And normally we would do this activity in class, but for today, we're going to try to do a version of it online since we're e-learning. So, do dolphins ease depression? So there's this idea of whether or not swimming with dolphins can actually help alleviate the feelings of depression. There's a video that, here's a YouTube link to in the PowerPoint, and then there's also a little QR code you can scan of a little news program where they interviewed people concerning this if you're interested. So, swimming with dolphins can certainly be fun, but it is also therapeutic for patients suffering from clinical depression. To investigate this possibility, researchers recruited 30 subjects aged 18 to 65 with a clinical diagnosis of mild depression. Subjects were required to discontinue antidepressant drugs or psychotherapy 4 weeks prior to the experiment and then throughout the experiment. These 30 subjects went to an island off the coast of Honduras where they were randomly assigned to one of 2 treatment groups. So we know it's an experiment because you can see that random assignment to treatments. In an observational study, these people would have been selected in place and then compared. But because we assigned them, that makes it an experiment. Remember, because it's an experiment with random assignment, we should be at the end able to determine cause and effect if we've set up our experiment properly. Both groups engaged in the same amount of swimming and snorkeling each day, but one group, the animal care program, did so in the presence of the bottlenose dolphins, and the other group, the outdoor nature program, did not. At the end of the 2 weeks, each subject's level of depression was evaluated as it had been at the beginning of the study. All right, so we can see some control happening here. We want to make sure that it's not the swimming and snorkeling and the being in the water that affects the depression levels. So both groups are doing that. And the only thing that's different would be the presence of those dolphins. Okay. So what happened after the experiment was over, we noted that of the 30 people in the dolphin care program, the 15 people that in the dolphin care program, 10 showed improvement. And in our control group, which was our outdoor nature program, only 3 out of the 15 showed improvement in their levels of depression. So that gives us 13 people who improved overall. Okay. So it looks like the dolphin care program really did help. It looks like, over 3 times as many people improved. But I have this question. Let's say those 13 improvers would have improved no matter what. What happens if those 13 people would have improved because they got a vacation or because they spent some time in water, and it didn't actually have anything to do with the dolphins that caused that number to be large, but rather it was just the random assignment. So in other words, if you think of these people as a big group of cards, and there are 13 blue cards and 17 green cards like you see in the pile, if we were to have randomly sorted those 30 cards into 2 piles, could we have ended up with 10 of the 13 improvers just randomly assigned to the dolphin group? Kind of like if I split the people in 2 groups, would it be possible to have more men in one group or more women in one group? Or would it be possible to have more young people or more old people? So just due to random events, sometimes we see streakiness or we see uneven splits. Just like if you flip a coin, maybe you flip a coin and get heads 3 or 4 times in a row. Okay, sometimes this unevenness happens. Okay, so could those 13 people just have improved anyway, and it was being there in the water, being there on vacation? What is that? So my question is, how likely is it for 10 of those 13 people to be randomly assigned to that dolphin group? For 10 of those 13 people, could this have just happened by chance? Now, if we were in class, I would actually give you cards. You'd divide them into 2 piles of 15, and you'd count how many people were improvers out of that dolphin group. But for now, we're going to use an applet. Now, there is a link to this applet in your in the Schoology folder. There's also a QR code to take you there if you want. And when you look at this applet, you're going to bring it up with this link, and it's going to say Analyzing Two-Way Tables. You can see our dolphins and control group over there, and you're going to do a couple of things to set it up. The first thing is in the bottom left corner, there's a thing that says Statistics, Difference in Proportions. Now, we will be interested in that later in the year, but for right now, I want you to change that so it says Cell 1 Count. Basically, what we want to know is how many people improved out of the dolphin group. Okay, when we do our trial. The other thing you're going to do is up here in the upper right corner, you're going to click Show Shuffle Options. Show Shuffle Options. And when you do that, it's going to bring up a graph. All right, so when you bring up that graph, you're going to, down at the bottom, you're going to count the number of samples greater than or equal to 10. So you're going to fill that in. And then you're going to proceed to press shuffle, okay, multiple times, and it's going to show you how many there are there. Okay, and I want you to run this sort several times and see, did you get any values of 10 or more? Okay, and then I want you to change the number of shuffles to 1,000 and figure out what is the percentage that are 10 or more. Now, I'm going to pause my video here for a second, and you should pause the video as well. And I want you to go where that applet is. There's a link in the folder, and I want you to run this a couple of times. Okay? Okay, so here I'm on the applet page. I'm going to change this to be cell 1 count. I'm going to show shuffle options. Okay, I want to count the number that are greater than or equal to 10 because we want to know how likely is it to get there. All right, so I'm going to hit shuffle. Here's me shuffling a card. That time I got, looks like 8. So I'm looking for this group A success rate. So 8, you can see my little sticker going on the picture. All right, I'm going to do it again. Shuffle, shuffle. So I'm up to, can you imagine us doing this in class, putting little stickers on the screen? You know you like those stickers. Okay. Right now I've done 10 trials and I haven't gotten any that are greater than or equal to 10. So it looks like if these people were randomly sorted into the groups that it doesn't seem very likely to get less than to get 10 people like we did in our real experiment. Here's 1,000. I'm going to shuffle again. Oh, I'm going to do this a couple of times. Look at this. All right, so I am getting some results that are greater than or equal to 10. Out of over 10,000, I have 139. So we're talking about just a little bit over 1%. A little bit over 1%. So what this is saying is the chance of getting 13 people who would have just improved anyway and just getting them randomly sorted into the dolphin group, there's about a 1% chance of that happening. All right. Okay, so did I get any values of 10 or more? Not on my several sorts. My first 10 I did not. Okay. However, when we do the number of shuffles, 1,000, here's one I did earlier. I did 5,000 different shuffles and I got about 1%, a little bit bigger than 1%, somewhere between 1 and 2. You should have probably gotten a similar result there. Okay, so the chance of getting 10 of the 13 improvers in the dolphin group by chance alone seems to be very, very low. It's less than 2% chance. So what this is telling us is that this is evidence that the swimming with dolphins seems to help with depression. We don't think that this happened just by chance. The idea of getting 10 of the 13 improvers in that group solely by random assignment is a very small possibility. So small that we think what's more likely is that the dolphins actually helped. All right, so this idea of simulation, like we did in the previous probability section, and trying to use this to make decisions, this is what our second semester is going to be about. But today, we're going to talk about probability distributions. Now, I actually had some administrators and some teachers come in and help. We did this in class today, like they weren't really in class, but they came to my classroom, and I had them do this by hand so that I could make a poster, because you know I love posters, so that'll be up in the room. So you can see, here's their results. And again, we didn't have anyone out of about 80, 90 trials of doing this that came up to this result. So it happened in person, even if it, just like on the simulation. All right, so random variables and probability distributions is what this is about. And how this connects to us is that a random variable is a numerical variable whose value is the outcome of chance. So when we were sorting those cards and we were counting the number of improvers out of 15 patients, okay, that number, that count of X, that is a discrete random variable. That is the result of chance. When you roll a die and you count the number of dots on the top, that is a random variable. So we're looking for a numerical outcome of random behavior, not categorical, okay, but some sort of random result, okay, and it's numerical. Now, for example, the Lucky Lovers discount. A local restaurant, the Nook, offers a Valentine's Day discount called the Lucky Lovers Special. When the waiter brings the check, he also brings the 4 aces from a deck of cards. He will shuffle them and lay them out on the table, and the couple will get to turn 1 card over. If it is a black ace, the couple will pay the full amount of the bill. If it is the ace of hearts, the couple will receive a $20 discount on their bill. If the ace of diamonds, at least it's the right color, they get a second chance to select one of the remaining cards. If that card is the ace of hearts, they receive a $10 discount. All right, so the goal is ultimately we'd like to be able to answer questions like what's the average discount per customer, or what's the typical amount that we would expect to give away on this discount. So to start off, what are the possible values? Now, this is going to be a numerical variable because X is going to represent the amount of the discount received, the amount of that discount received. That answer could be $20, $10, or $0. This is numerical data, and the result, that $20, $10, and $0, is a result of a random experiment. It's based off of chance of what they get when they draw these ace cards. Okay, so my variable, the amount of the discount, possible values 20, 10, and 0. So what we'd like to do is we would like to see what are the probabilities of each of these events. Okay, so we know that a discrete random variable can only take a countable number of values. In this case, we've only got 3 possibilities. It's a finite number of things there. It's not a decimal, it's not a measurement. In this case, we're using this discretely. Each value is going to have a probability associated to it, and we want the probabilities, if we're talking about a distribution, to add up to 100%. All right, so how would we do this? So we know that to get the probability of getting a 20, now notice this notation here, P of 20, that's like saying the probability that X equals 20. All right, would be the same as getting the first card being the ace of hearts. Now he said he was going to bring the 4 aces, so there is a 1 out of 4 chance of getting the ace of hearts. That is a 25% chance. So I'm going to write that in for my probability there. Okay, now the probability of getting a $10 discount. In order for that to happen, the first time you get to get the ace of diamonds, so you get a second chance, and then you get to pick from the leftover cards, and that second one then has to be the ace of hearts. Okay, so there's a 1 out of 4 chance of getting that ace of diamonds the first time, and then there'd be 3 cards left, the 2 black aces and the ace of hearts, so you have a 1 out of 3 chance of selecting that ace of hearts. Now remember, that's a dependent conditional probability ace of hearts that second time. That's why that number in the denominator has gotten smaller. So 1/4 for the first one, 1/3 for the second, we multiply, we get 0.083. All right, now if I'm going to talk about the probability of 0, now several different options here. It could be that the first card was one of the black aces, or that the first card was the ace of diamonds and then you got a black card the second time. Now we could go through and calculate these and put them together, but we also know that the sum of the probabilities should be 1, and right now we have everything except the last one. So what's going to be easier is to take that 100% and subtract off the 2 we already know and get that that's about 67% there. Notice this is a probability distribution. We have our random variable X, which is a numerical variable, and we can see all the probabilities associated with all the possible outcomes. The only difference between a probability distribution and the probability like we talked about in the last chapter is that instead of just talking about one possible outcome, we would like to see all the possible outcomes and what those probabilities associated with those are. Okay, so one thing you need to be able to tell the difference between are discrete and continuous. We talked about this back in chapter 1. Remember that discrete is the values, it's a collection of isolated points on a number line. A discrete is what you normally get as a result of counting. But generally we're looking for kind of like counting numbers, whole numbers. There's usually a how many kind of an answer. It's a countable, finite number of values. Examples would be like the number of parking tickets issued this week. I should be able to count that. In this chapter, we're going to be talking about 2 special types of discrete probability distributions in section 7.5, binomial and geometric distributions. Okay, more on that later. Continuous means we're talking about an entire interval of numbers. Generally, these are the results of measurements happening. For example, the time in seconds to react to an accident. Normally, you've got lots of decimal answers that are possible. It's not whole numbers. It looks more like a range of values rather than isolated points, this one, this one, this one. Special types of continuous probability distributions include the normal distribution, which we've already talked about, and also what we're going to talk about at the beginning of next semester. All right, now for probability distributions, we are pretty much for the rest of this year going to be talking about discrete probability distributions. In other words, we're talking about numerical counts, okay, like counting the number of people who improved out of those 15 people in our dolphin group. And we want to know things like how likely is it to get a specific value of X? What's the typical expected value of X? What's the most common value of X? Is there a lot of variation? Is there not a lot of variation? So a couple of things to keep in mind. Okay, the first is that remember that there's two rules for probability all the time, and that is that each individual probability needs to be between 0 and 1, and that the sum of the probabilities need to add up to 1. When we're talking about a probability distribution, again, P of X, we're talking about it in terms of the long run relative frequency. If we were to perform this experiment many, many, many times, we would expect the proportional results to equal that probability. Also, just a general note here. A lot of times we're not going to say X equals 2, we'll just say probability of 2. And that means that your variable equals 2, so it's a little shorthand just to be used to. Also, a probability distribution, remember distribution, how is 100% split up amongst what I see? That's that sum of X 100% there, can be represented as a graph, a table, or a function. So the idea is, let's say that X is the number of dogs and cats kept as pets in several randomly selected homes in Avon, Indiana. So I went and I asked, how many pets do you keep in your house, dogs and cats? And we got these answers over here. If I wanted to turn this into a probability distribution, then I would need to turn all of these raw counts into their probabilities, P of X. So the first thing I need is the total. Looks like we interviewed 150 people. So to get those first two probabilities, I would take the frequency, 20, out of the total, 150, and I would get my probability. You should use at least 3 decimal places for these or leave them as fractions. So 0.133. And then for 1, I would do 35 out of 150 and get 0.233. I'd continue for the rest. 50 divided by 150, 13 divided by 150, etc. And that gives me all those probabilities that are left. Notice that these should add up to 100%. Now, if I wanted to show the probability distribution, then I would put the probability on the vertical axis, okay? That I noticed my highest one was 33%, so I just sort of went by 5%. That should be scaled up to about 40%. And then I would like my variable, which would be the number of pets kept, to go on that x-axis. Now, because I'm going to draw a bar graph, instead of putting the 0 and 1 and 2 on the hash mark, I just put it in the middle of where I'm going to draw the bars so I can use my graph paper a little easier. Okay, and then I would make the height of each bar go to that probability. So for example, 0, see the bar is centered at 0, goes up to about 13%. Okay, and I can graph my probability distribution. Okay, so probability distribution can be represented by a table. It can be represented by a graph. The key there is that the vertical axis is the relative frequency or the probability of that event. The other important thing is that you have all the possible outcomes. So not just 0, 1, 2, but every possibility should be included. All right, now you should be able to answer questions from probability distributions like what's the probability that a randomly selected household will have 4 pets? Right, so we should just be able to say, well, the probability of 4 is 0.147. What's the probability that a randomly selected household will have no more than 2? No more than 2 means less than or equal to 2. Okay, and you should show this addition, show putting those pieces together, or you run the risk of losing points on the AP exam for not having sufficient work. So I want to put 0.133, 0.233, 0.333 together to get my answer of about 70% there. All right. So when we're talking about probability distributions, they will provide information about things like shape and center and spread. So in other words, because this is numerical data, X equals 0, 1, 2, 3, 4, 5, 6. That brings our old friend Soxbacks into play. All right, so just like chapters 1, 3, and 4, we can talk about things like shape. The shape of this distribution looks like it's unimodal with a peak at about 2 pets and looks like it's slightly skewed to the right. Remember, you want context, distribution of number of pets. We have our shape skewed to the right because it looks like there's slightly more bars. It's sort of drifting off onto the right side. We could also talk about outliers. In this case, there are no outliers, so I wouldn't even mention them. Got my My data there is weird. So as far as center goes, I would be looking for the median. Forget my little PowerPoint mistake there. Median would be about the 50th percentile. So I think, okay, 13-ish percent, 23-ish percent. That puts me at about 36. If I go up to the second bar, I should hit the 50th percentile at 2. And if I want to talk about spread, the range is going to be from about 6 minus 0. The range is 6. If I wanted interquartile range, I would be looking for the 25th and the 75th percentile. 13% isn't quite enough. To get to the 25th, you'd have to go into that bar where the 1 is. And then if I work backwards, I want 25% from the top, 0.007, 0.06, 0.147. That's only 21%. So to get to that 75th percentile, I would need to go to the 3 bar. So 3 minus 1, my interquartile range is about 2 there. And those are estimates. Okay, so when we're talking about our probability distribution, here's one. I've got number of cars, discrete. I've got my probabilities. Notice they add up to 100%. Here's the graph I made in my calculator for this. Isn't it beautiful? One other piece of information you may need is something called cumulative probability. So the cumulative probability can be represented as a table or a function or a graph, and it's the probability of being less than or equal to the value of the random variable. Okay, so for example, if my number of cars is 0, I have a probability of 0.03, which means the cumulative up to that is also 0.03. If I want the probability of 1, cumulatively, it'd be up to and including 1, that's 0.3 plus, 3% and 13%, that gives me 16%. Okay, similarly, if I'm talking about 2, okay, 3% and 13% and 70% give me 86%. So the probability that something is less than or equal to 2 would be that 0.86. Okay, if I wanted 3, I would add up everything up to and including 3. That would give me 0.96. And again, up to and including 4 would be all of it. So this last number in a cumulative probability distribution should be 1. Here's an example of what that might look like. You'll notice that this cannot be a plain old ordinary probability distribution. I would know that by looking at it because these probabilities of these bars are all greater than 90%. There's no way those can add up to 100%. This last bar adding up to 1, okay, gives me the clue that if it wasn't mentioned that this was cumulative, that it probably is, if I think this is a probability. All right, so what do you need to know then? So a random variable is a numerical result of some random process. Okay, this is like us trying to decide how many improvers there were out of our 15 people swimming with the dolphins. Okay, I'm usually looking for a discrete random variable. In the next several lessons, that's what we're going to do. We're going to be counting things, the number of, how many, etc. Remember, discrete is usually the result of a count, whereas continuous is usually the result of a measurement. All right, a probability distribution is going to show the probability for each possible outcome of our random variable. The sum of these probabilities should equal 1. That word distribution is showing you how 100% is spread over all the outcomes. The only thing different about a probability distribution versus what we were doing in the first several sections of chapter 6 was that now we're finding all of them. It's not just one, but I want all the possible outcomes. Remember that your probability distribution can be a graph, a table, a function. That means it could be an equation. There are times when you can model that with an equation. We'll talk about that more later on. And then since your variable is numerical, when you go to talk about it, you're going to describe it using SOCs, just like we did in chapter 1, 3, and 4. Don't forget your context. You always want to mention their variable using the actual words. If your problem's about puppies and kittens, you need to address puppies and kittens when you're writing. All right, and then remember that your cumulative probability distribution, that's going to show the probability that x is less than or equal to some value. So that's like, if I want to know the cumulative probability of 5, of x equals 5, then I would say, okay, that's all the probability up to and including 5. Okie dokie. So if you have any questions, please let me know.